Alright, welcome to homework 42. It's the last homework assignment of the semester. We're going to be going over problems 3 and 8 from section 11.4. An aluminum pipe column has a particular length, elasticity, inside and outside diameters, and it is supported only at its ends and may buckle in any direction. Calculate the critical load for the following conditions: pinned, fixed free, fixed pinned, and fixed fixed. So this is the equation that we're using, except now instead of just dividing by L squared, we're dividing by L equivalent squared, where our equivalent length is going to be our initial length times some K constant. And our equivalent has to be this shape. This like bendy shape, this open parentheses looking shape. And I recognize that's really confusing, so I'm going to do all four A, B, C, and D at the same time, and we're going to compare them. So if I have my A is pinned, I have my pins at my bottom and my top. For B we have fixed free, so it's fixed on the bottom, it's free at the top, and the rest of the scenarios. If I have some force at the top and I push down, and we're looking at A specifically here, if I push down, due to the fact that it's only held together with a pin, it's going to bend and make this curl shape because it's free to have any slope at its tips. However, for the rest of them, they're going to make different shapes. So if we look at B, the bottom is fixed, so whenever I push down on it, it has to bend in some direction and it'll have its freeing over the top. For C, it has to also keep that location in the middle, so it has to bend over and then around like that. And for D, due to the fact that it's fixed on both ends, it makes a weird shape like that. So for our K value, if I look for part A, my little C-like shape is the same as my length equivalent. So my K equals 1. For B, I have 2 of my little shapes in my equivalent shape, because my little curl there, if I extend it on the bottom all the way out, then I'll make that kind of parenthesis shape. C, I have 0.699. If you're wondering where on earth did 0.699 come from, I have no idea. That's what the textbook says that value is. And then for D, we have a lot more than just that parenthesis shape. It keeps going past that, so if you multiply it 1/2, then you'll get your length equivalent. So we have the following K values, and that's what it's going to tell us what we're going to plug into our P critical, because that is our length equivalent, which is our length initial times this K value. So like for part D, if I have my initial length of 10 feet, but it's fixed, then only half of it is necessary. Half of that length is necessary to make this little parentheses shape. That's what gets squared, and we divide that from pi squared EI. So I can plug in all of my information. I have pi, pi is just a constant. I have E, I can solve for my length equivalent for all 4 scenarios. I, my inertia, that's the same, it's just a hollow circle, so it's the same inertia of doing this for a long time for all these hollow circles, so we can plug that in, and once we plug in these K values, these are the answers that you're going to get for A, B, C, and D. A vertical post AB is embedded in concrete and held at the top by 2 cables. The post is hollow. We know the modulus of elasticity, the outer diameter, and the thickness. The cables are tightened equally by turnbuckles. If there is a factor of safety of 3 against Euler buckling in the plane of the figure, what is the maximum allowable tensile force in the cables? So, first, I'm going to make a free body diagram, because that will relate my critical load with my tension of the cables. So I'm going to say if I have a vertical tension, the vertical component of my tension is 2 of them will be counteracting 1/3 of my critical, and the reason it's 1/3 of it is because that is my factor of safety, and so it's only going to do 1/3 of the maximum force. Then because this t vertical is not super helpful because we're looking for t total, I'm going to say t vertical is t total times my length divided by some distance, and this is not my diameter distance here, this is my diagonal. Sorry, it is not my diameter, it is my diagonal. And L is the initial length of my vertical post. And then P critical, we just have our generic equation we've been using this whole time. So diagonal we can find with Pythagorean's theorem. My equivalent length we can find with the height of the vertical post times some k. And now we have to ask ourselves, what is our k value? So let's look at this. We know it has to have some fixed bottom, but the top, this is where things are we have to think about it. So we have two cables. Can it be this one? If we have it, say, free at the top, and we know it's connected to the cables, and if it's bending over to the left like this, then the cable on the right side is going to be in way more tension, and so it would pull it back to the right. So it can't be this one. If we look at the next one, that might make sense because we just found out that it has to stay in the middle. However, our tension cables don't care if it is forced to be flat at the top. So the fact modeling it as being fixed on the top would not work. We could try this one where it's staying in the middle, but the rotation can be anything we want it to be, and that will work for our model here. It is a fixed pinned beam, which means our k is 0.699. Now, when we plug our k into our L equivalent, we plug our L equivalent in our P critical, and then we set our relationship with our P critical with our T. We can get this equation, plug everything in, and get our answer of 18 kilonewtons. So this is almost the exact same equation that we used last time, except last time we had to use pinned in our homework problem, so our L equivalent was the same as our L initial because k was 1. So not too much is changing here, just again make sure you understand how to use this equation and how to find your k value, and that is all you need for this section. I hope this was helpful, and good luck on your homework.